Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome to the next class of CS103 computer programming, where we are going to discuss the recursive algorithms in detail, and we'll see some examples of recursion. There's some codes that are related to recursion. So this is like a basic concept of how recursion works. You've seen that in the lecture, what recursion is and what are recursive algorithms. So now we'll start applying them on typical recursive problems, and we'll see uh, how the um, recursive algorithms work. What is the basic phenomena? How do you declare a recursive function, and how does it differ from a typical iterative code? So let's see now the code, which is, I hope, shared on the screens now. So if you look at the first code, the first problem that we're going to try to solve is the typical factorial problem. And you know that in the recently conducted lab of this week, actually you have already seen how to compute the factorial using a typical iterative for loop. In this lecture, I'm going to tell you how factorial can be computed using a recursive function instead of an iterative for loop. So if you look at the code now, and I'll just go through it one by one, line by line. So initially, again, you initialize some of your very header files. Then you have got these namespace using namespace command. Then you have got a function that is declared as int factorial, and it takes an integer as its input. Notice that it is returning a data type int, and it is taking a data type as a parameter, it's taking an integer. Then if you look at the main function here, this is how it's going to run. Then you see out factorial of 6 is, for example, whatever factorial of 6. So this is the function call of a recursive function. You're basically saying that the initial input for this number, the initial value, the first value for this is 6 only. This is then followed by another call, which is for 10, and both of them will be evaluated separately. But let's see what the function does. And this over here is what we call a recursive function. We call it recursive because you notice that its name is fact, and inside some place it is calling itself again. So this is what we call direct recursion, and this is the exact direct recursive function. The function is calling itself again and in some piece of its code. So let's go through the factorial code. Let's go through the function that is going to return you the factorial. So in here, you'll notice that this is the base condition. We know that if factorial, if you want to find the factorial of 0, so if the number that is input is 0, well, simply return 1, right? Otherwise, if this is not true, then this part is what we call the general case. And in this general case, what you need to do is you need to simplify your problem a step. So our simplification is that we are going to decrease it by 1. Those numbers are going to be decremented by 1. And again, the function call is made on top of it. So this is going to call factorial of 5. And you multiply it with 6. When you call the function, actually the multiplication is something that will happen at a later time. So it kind of, this function, this factorial function is kind of stopped here. It is paused here, and it is paused until you retrieve the result of factorial of 5. And factorial of 5 is a new function. It has its own memory, its own local variables. It has to run with factorial of 5. It runs there. It gives us an answer. It does not match the base condition, and it is then going to try to get 5 multiplied by a factorial of 4. And this cycle continues on until there comes a time when you'll finally reach the point where you'll get the values. So again, once the base condition is matched, then the reverse process starts. And once the reverse process starts, we now know the value of factorial of 0, which is 1. So 1 multiplied by 1 is what is going to be returned as factorial of 1. Once we know the factorial of 1 is returned as 1, we know that since that was called by factorial 2 function, so we know that now we are going to return 2 multiplied by 1, which is 2. So factorial of 2 is 2, and so on. We'll keep on feeding the correct function until you basically reach the final call, which is factorial of 6. In that case, it is 6 multiplied by factorial of 5, which we now know is 120. So 6 multiplied by 120 is going to be 720. That's the final value that gets returned and printed over here then. So notice that once the base condition is in a true factorial function, we actually are initially going in one direction from by using function calls, you're going down, 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 right? And ultimately, once you have reached the final call, then you go back out, right? So that is how a typical factorial function works. So let's just run the code and see if we get factorial of 6 and factorial of 10 as the right values. So factorial of 6 should be 720 as is expected, right? And then factorial of 10 is 3628800. And this is the exact answer we were expecting over here, right? So let's clear all and let's note the difference over here. So the difference or the point to note is that in all of these commands, what we observe is that the function is just calling itself. So this is a really simple function. Once you master the concept of recursion, then the code is very simple, very short and sweet. However, it is hard to understand, and that's the thing here. So this, if I put it like factorial number minus 1 multiplied by num, it would have behaved slightly differently, although the result should still have been the same. But changing the order of this if and else would have made the problem totally different. So for example, if I put this if num is not equal to 0 and I do this, otherwise return 1, then it would have been stuck in an infinite loop maybe. So these are some of the things that you need to be extremely careful about. That the recursive function is always present, and this, by the way, is tail recursive function. As you can see, this is the last command that gets executed, right? So there are these different kind of recursions as we have already seen. So let's go to the second example after factorial, which is slightly more complex, and that is the Fibonacci number series. A Fibonacci number series is a series that starts from the first two characters, and basically, the third one is basically the sum of it. So you need to calculate n different numbers together for the Fibonacci series, such that you basically add the first two numbers. The third number is the sum of the previous two numbers. The fourth number is going to be the sum of third and fourth number, and so on. So in that case, if you want to find the Fibonacci sum of let's say the nth integer, you're going to use this particular piece of code. Here again, you ask for the first Fibonacci number, the second Fibonacci number, and basically enter the position of the desired Fibonacci number, the value n, right? So you determine the nth value, and then you say the Fibonacci number at position nth is, this is a function call. Again, a simple function call which takes 3 parameters, int a, int b, and int n. So nth position in the first two alphabets. If it says that n is equal to 1, we simply return a. If n is equal to 2, then we simply return b. Otherwise, we return, now there are two function calls here. First function call is for a, b, n minus 1. And the second function call is taking the sum of Fibonacci numbers of a, b, n minus 2. And we know these two different calls basically mean that first, when this call is made, it will keep on going down until basically it reaches a particular value, right? On the other hand, this one is a different call, and this one is again made, which is going to, this one basically moves in one by one. This one is going to move by two values at each step. So again, a simple code. However, in this case, there are two base cases, n is equal to 1 and n is equal to 2. For both base cases, there's a different behavior. But this one, this portion over here is what you call the general case. And if you execute it, you'll notice that let's enter the first number as 1 and second as 1, and let's go for a certain value, right? So let's enter the first Fibonacci number as 1, let's enter the second Fibonacci number as 1, and let's enter the number of desired Fibonacci number as 10. So the number at position 10 is 55, and I can kind of get to this, that this is basically saying that the number at position 3 is going to be 1 plus 1, 2. Position 4 is going to be 2 plus 1, 3, right? Position 5 is going to be 3 plus 2, 5. And then I think it's 5 plus 3, 8. 8 plus 5, 11. 11 plus 8, 19. 19 plus 11, 30. 30 plus 19, 49. right? And so on. So ultimately, this is going to reach a point which is going to be 55. So it's just the sum of the previous two values, and that's how the series is progressing. And we'll notice that if you calculate these values, final value at position 10, you'll probably get to 55. Yeah. So I think if we then move on to the next example, which is again um, slightly, I think, or equally complex here, as you can see. This basically finds the largest element in an array. And we know that to find the largest element in an array, you've already seen that we can use an iterative function, a for loop, to go through each element of the array and find the largest element. However, you can also do that through recursion, although it's not very apparent, how you're going to do it. But here's the idea. The idea is that you declare an array like of int array of type int and having 10 different elements which are initialized as 23, 43, 35, 38, 67, 12, 76, 10, 34, and 8. And then our goal or main aim would be to somehow get the largest element in the array, and we just call this function largest int array 9. Then if you move on in largest, if you move into the function, we notice that we pass it a constant list. We pass it the lower index and we pass it the upper index. So int max is if you finally reach the single index, then that value is the largest value and we are fine with that. Otherwise, so in this case, if the value if both values are equal, then the size of the sublist is 1, and we basically say that simply return the list of lower index. So simply return the value here, and that is probably the max value here as well. However, on the other hand, max is the largest. So max is, again, you call the same element again of list, lower index plus 1 and upper index. So whatever your lower index is and whatever your upper index is, you ask it to find the largest values within that region. If the result that is returned from this is greater than or equal to max, then simply return this value. Otherwise, return the value of max. So this over here is what is the post-processing. And this, as you can see, is not a tailed recursion taking place, because there's some piece of code that is even running after the function call has been made. And what's noticeable here is that what you are actually trying to do is something which we call the binary division. So at each point, we are trying to divide it to basically using a lower index, and you're incrementing the lower index constantly, right? So the lower index is always going to be increased. If we have reached the upper index, if we reach the final point, then we are done. Otherwise, you need to check each and every single component and keep the max in memory. However, as you can notice, this is not an efficient way to compute or get the largest member of an array. A simple for loop would have done far better. And I think in my personal opinion, I would always say that a for loop here is more intuitive, simpler to execute. And I feel the right way to go as well, right? So although we can do this with recursion as well, but I am not going to recommend you to use recursion. Actually, wherever you can use a for loop, you can equally use a recursion there as well. And this is one example which is where it's not very intuitive to use a recursion or recursive algorithm. However, as we see here, recursion works absolutely fine in this case. So then let's go to slightly more complex examples. And these are more complex in the sense that the recursion here is not absolutely clear. So for example, let's go to the code where we want to convert a binary integer into its corresponding into its corresponding decimal integer. Or even before that, let's just run this program once so that we know what the values are. And we notice here that if you run it, the largest element is 76, and indeed the largest element in this list is 76. So this code works absolutely fine. However, it's not very intuitive, and I am not going to recommend this. I am always more in favor of these kind of problems which are much simpler, and over here it's more intuitive to use the iteration approach than a recursive approach. But here's an interesting part. So Again, this is a binary to decimal conversion, something that you're already aware of since class 5 or something. And you've also done this or have seen part of it in your chapter 4 of your discrete structures lectures. So there actually you use an iterative approach, the for loop, to solve this. But this can also be solved using recursion. And here's an example of how it is done using recursion. Again, I would say that this is not very intuitive to use recursion over here. And it's much easier to use to do it in an iterative manner. Also, in terms of efficiency of the program, I think the iterative program is better. But since the problem can be solved using recursion, and if it is forced upon you to use recursion in a particular place, I think this is the way to go. Personally, I will never force recursion on you. But then again, at some places, it's obvious that recursion is the way to go. For example, in factorial, for example, in a lot of other problems as well. So let's see this particular example, and let's see what we can do over here. So again, this is basically initializing some variables. Decimal number is equal to 0, bit weight is equal to 0. Cout enter number in binary, so you should enter some number in binary, and then it basically just passes the binary number, the decimal number, and the bit weight to this function. Notice that this is void, so this must be exactly like these two variables that are changing continuously inside the function, and the final result is going to be, I think, simply maybe written out or returned in basically the decimal number. So in decimal is going to be the one that contains your result, as that is exactly the case, as you can see in the cout statement over here. And this is what is happening. So these two are variables that can be changed, who are passed by reference and whose values are continuously changing. We initialize it by bit. If binary number is greater than 0, so if the binary number that is passed is greater than 0, then in that case we simply divide it by 10 and get the remainder. The remainder is basically stored in bit. The decimal number is then calculated by using the bit, the original decimal that's still there, added to bit multiplied by 2 raised to power of the weight, whatever that is. So we start with 0 at the start and increment it by 1 with each run. The binary number is then updated to a binary number divided by 10, so that basically the last bit is being removed at each point, and the remaining number is the binary number that is left. Increment the weight, we again make the function call. So this is the last command that gets executed, and we notice that the weight has been incremented by 1. The decimal, we have already included the bit that was added at the last. So this is like you take the last bit, then second last, then third last, and fourth last, and so on. So you can using those and updating based on 2 raised to power of whatever values you are taking. And finally, the binary number is being updated by continuously being divided by 10 in this piece of code. So if you notice, all that this code is doing is that perhaps it appears that there is no what you call base case here, but this is the base case. So if this is not true, of course you don't need to run it and simply return. And when you make this return, you're going to return all the way back. So this is your base case. However, when this is false, then this is your base case. So this else, the missing else here, is your base case in reality. And this one is what I call the general case. So whenever binary number is greater than 0, it's going to execute this code and ultimately make a call back to itself until it basically there comes a point where the base case is matched, where we reach this else. And once you go into this else, you actually don't need to do anything and simply return. So I could have written over here else return, right? And now you notice that this else is what is acting as your base case now. So let's just run the code and let's feed it a binary number. Let's call it 111, and we know that 111 then evaluates to basically, I think 7, and that's exactly what we get over here. So 111 is equal to 7, right? So let's just run it again and let's see what value do we want to compute. Let's try for a lot of ones. And let's see what the values are. So this is equal to 2559. And notice one thing. So this is where we have overran actually our allowed space for int. So it cannot store this larger integer. And in this case, I think a long or something else would have been a better option. Anyway, since we are, I'll enter a value that is kind of valid for now and see what the results are. So for 8 ones, I think the value of 255 is the right one, and so on. You can keep on doing this for as long as you want. You need to understand the program and what this is doing. The opposite of this is what I call decimal to binary, and this is much simpler because the only thing, it's the same code here, but the only thing here is that in this case, you are making this call first actually and outputting the remainder after it. So this is like you basically want to output the first one first, then the second one, then the third one. So you actually divide it by 10 at each time. So until there comes a point where the number is equal to 0. In that case, whatever is the base will be simply the last integer will be returned, and so on. So this is really simple code, and all it does is it converts a decimal number to its binary number. And we'll see that, for example, number decimal is, let's call it 8, right? And in binary is 1000. That is exactly the one that we are seeing over here, right? So similarly, we can actually try this code. This is simpler, looks cleaner, but this has its own complexities. This has to be placed before it or after it. The order does matter over here. If you print it earlier, you'll actually get answers in reverse, right? So the order in this particular code in a recursive call is in particular is very important, and you need to be sure that you're making the recursive call in the right order. And finally, let's go to a more complex example, although it's not as complex. You must already know about the towers of Hinoy problem. So this is a really simple problem where you actually have got 3 disks which are correctly placed or incorrectly placed, right? And you basically want to put the higher one before the the one that is more thicker actually at the bottom, and the one that is thinner at the top, that is the thinnest at the top. So in this case, in this simple example, we have got 3 needles that we want to put together, and we want to move them in an order that we want to calculate what moves we have to make to actually get them in order. This is a typical Tars of Hinoy problem. And we see that if you use recursion, this is really simple to solve. And we'll see how. Although the recursion here is kind of complex to get, and I really don't expect you to be enough to have mastered it enough that you can kind of come up to this piece of code on your own. So let's start. The idea here is simple. You have a function move disks, which calculates counts, right? And then it takes the needles and determines if a particular move is possible. The idea here is that by recursion, actually you are checking all these different options and returning back if an option is invalid. So the idea here is moves for 3 disk problem are going to be move disks 9. So that's the first thing. Then count is 9. And 132 is the order of the needles, right? So 132 is the order of the needles. So in this case, what we do is we move disks count -1, we decrement. So this runs so that we can see that this is a recursive function because it has a move disks utilized 2 times. So these function calls are being made twice. First, it makes this one to call it with needle 1, 2, and 3. And in the second part, it again makes the same call, but now this time with needle 2, 3, and 1. So the order has changed. And this is a typical Tau of Hinoy problem. So let's start and run it. And what we notice here is that these are the different steps that you need to perform actually to get the disks in the correct order. Notice that the cout that we are retrieving from this are because each of the call 9 steps, and each of that is made twice, right, for each step. And inside again, because of the recursive function, once you decrease it for 8, it is again made twice, right? So for 9, it is made twice. For 8, it is made twice. And this is a product here actually, because for 9, it's not actually made only twice, but it is 9 raised to power. Sorry, twice 2 into 9, right? 2 into 9 for 9, 2 into 8 for 8, 2 into, and again 2 into 8 and 2 into 8 twice, because that call is made twice for 8, and so on. So we notice that this is a huge number, and that's why we're getting so many possible solutions from this. So this basically ultimately will result in a case where you have tried all these options and finally you reach a solution such that the needles are correctly placed. And that is all, I think, for this particular lecture. The idea here is to show how recursion works. Some of these problems are very advanced and not easily, for example, stars of Hinoy is not something that you can easily get using, or you can conceive using recursion. Finding the largest elements in an array is something that I think is very much an iterative problem and should be solved with iteration rather than through recursion, although a recursive solution does exist for those kind of problems as well. So whatever is in an array can actually be searched or looked upon using recursion and so on. So I think these are some of the basic examples that will help you understand recursion more. Maybe if you understand the factorial, the Fibonacci number, and possibly the decimal to binary, or yeah, that was the easier one, but binary to decimal as well. If you understand those problems and how the recursion is working in those problems, you'll be able to use recursion in most of your programs. But this requires a totally different way of thinking, I presume, and you probably need to work extra hard to get the grasp of recursion. So with that, this lecture comes to an end. In the next lecture, I'll attempt to try to work with the STL, the standard template library, and the functions that are available in there, especially the random function, srand, and other things, and possibly discuss how to make header files and how to make the code files and how to connect both of them. So with that, I think my lecture on recursion and the basic functions and basic coding problems comes to an end. So just a series of everything that is related to coding is over. I think everything that is related to pure coding is now shared with all of you. And I really hope that you have learned a lot about programming until this point. So from now on, we'll just somehow merge these things together, and we'll talk about some more advanced topics, maybe like graphics, maybe STL, and maybe exception handling, the 3 topics that are left for this course in the coming lectures. I wish you all the best and see you soon. Take care. Allah Hafiz.